Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 1st, 2025, just 3 days ago. The standout result is a gradient-based early stopping method that speeds up transformer fine-tuning by between 1.57 times and 7.22 times, while also delivering about 1.2% higher average accuracy. The paper is titled GradES, Significantly Faster Training in Transformers with Gradient-Based Early Stopping, and the implications for model training are quite significant. In short, the method freezes individual attention and MLP components when their gradients shrink, avoiding costly validation passes and curbing overfitting. On X, one post calls the method a cool idea, praising layer-level early stopping when gradient norms drop, and noting experiments across various large language models support it. Engagement looks solid with about 135 likes. Alright, the previous figure set up the headline gains. Figure 1 shows why the method works by plotting gradient L1 norms over training steps for each projection matrix. The attention projections drop faster, while the MLP projections stay higher for much longer, which signals slower convergence. The red dashed line marks the freeze threshold, so any curve dipping below it gets frozen. This separation means many attention blocks can stop updating early, saving compute while MLP parts continue learning. Trigger text. Figure 1 shows why. Bounding box 0.06, 0.05, 0.95, 0.78. Alright. The previous figure highlighted faster gradient decay in attention blocks. Table 1 presents the payoff in accuracy and speed. The table compares full parameter, low RA, and their combinations with classic early stopping and with GradES across 5 models and 8 benchmarks, with averages on the right. The rows show that GradES often tops average accuracy while reducing training time, so efficiency rises without sacrificing performance. The QN0.6b and Mistral 7b blocks especially show gains, which reinforces the component-level freezing strategy. So the previous figure traced gradient drop patterns. Table 2 quantifies what that meant for training time and compute. Table 2 reports training seconds, speed up, floating point operations, and their ratios across 5 models and multiple fine-tuning methods. GradES consistently improved speed while cutting compute, which showed up as bold speed up and floating point operations ratio wins, especially when combined with low RA. The QN0.6b and Llama 8b blocks show over 2.8 times speed up with equal or lower floating point operations, so efficiency rose without accuracy trade-offs. Okay. The previous table quantified speed and compute. Figure 2 shows how freezing progressed during training across 5 models. The y-axis reports the fraction of components frozen, and the curves rise in clear stages, which indicates waves of convergence. Most models freeze about 30% near step 1000, then another large block around 1400, and finally approach full freeze by 1600. QN0.6b lags slightly, so model scale and architecture shape the timing. Alright. The previous figure showed freezing waves across training. Figure 3 charts the underlying gradient norms that drive those freezes. Figure 3 shows element-wise L1 norms over steps for MLP matrices in orange and attention projections in blue, with a red dashed freeze threshold. The MLP curves stay higher for much longer, which indicates slower convergence and justifies leaving them trainable while attention freezes. The shaded bands convey variability across layers, so confidence grows as the bands narrow toward the end. Well, the previous figure charted gradient norms. Table 3 lists the shared hyperparameters that made the comparisons fair. Table 3 shows learning rate, batch size, gradient accumulation, maximum sequence length, and the low rank for full parameter and low RA across 5 models. The settings remain consistent, which matters because speed and accuracy differences then stem from the freezing strategy rather than mismatched training knobs. The low RA rows use a higher learning rate and specify rank 32, while full parameter rows omit a rank. Alright. The previous table standardized the shared training knobs. Table 4 specifies the GradES choices per model and method. Table 4 shows a consistent grace period ratio of 0.55, which delays freezing so components adapt before thresholds apply. The threshold tau varies widely across models and between full parameter and low RA, because gradient scales differ and low RA factors need tighter cutoffs. These settings make the freezing behavior predictable while remaining tuned to each setup. Wrapping up, 2 takeaways stand out. Gradient-based early stopping at the component level trims training time by up to 7.22 times while lifting average accuracy by about 1.2%, and attention blocks tend to converge much sooner than MLP parts, which unlocks targeted freezing. The broader implication is cheaper, greener fine-tuning at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.